Good morning. Welcome to the 10th anniversary of the Kavli IPMU. So I'm Hiroshi Oguri, and I'm the chair of the organization committee of this 10th anniversary symposium. So the Institute for the Physics and Mathematics of the Universe, which is the original name of this institute, was established 10 years ago this month in October 2007 as a part of the World Premier Research Center initiative of the Ministry of Education, Culture, Sports, Science, and Technology of Japan. And in 2012, it became a member of the Kavli family of institutes worldwide. During the past 10 years, the Kavli IPMU has made remarkable progress, attracting international talent to Japan and producing several groundbreaking discoveries in physics, mathematics, and astronomy. To celebrate this occasion, we have gathered leading scientists and brought back some of our most successful former students and postdoctoral fellows to showcase the Institute's achievement over the past 10 years and to discuss future research direction of the Institute. So welcome to this celebration. So I'd like to start with opening remarks by our director, Hitoshi Murayama. Please.
Okay, thank you. And so welcome to the symposium. So this is a wonderful occasion for all of us that we are celebrating this 10th anniversary of the Kavli Institute for the Physics and Mathematics of the Universe. And as Hiroshi already said, the program looks great. We have so many prominent speakers, both senior and junior, and we're going to enjoy this meeting a lot, I believe. And of course, this institute is all about science, right? And all the talks about science. But at the very beginning of my opening remarks, it's a little bit of reminiscence talking about the past. And also towards the end, there are 3 talks reminiscing about how the institute got off the ground and how building got erected and so on. In between, everything's about future. So please bear with me. Just one talk in this morning. It's about how we actually got here. So this is actually the original slide I presented at the review committee 10 years ago. So we said we really need to bring mathematics and physics together because mathematics is the quantitative foundation for physics. And physics has provided a lot of inspiration, prediction, and conjecture for mathematicians. And this is a statistic, actually, Hiroshi came up back then, that since 1990 till 2007, 7 out of 18 field medals were inspired in some way by particle physics. Now the count is 13 out of 26. So the physics has a lot of influence on mathematics research. Then I told the review committee that combination of math and physics is there to study the universe. And we listed these 5 questions. How did the universe start? What it's made of? What is fate? What is fundamental laws? Why do we exist? And I told them that we need new data to address them. And for this purpose, we need to create new mathematics and new physics. And I listed all Nobel Prizes back then related to this area. And of course, since then, we have added 4 more, included one this particular year. So this has been a very exciting field. And for this purpose, I told them that we need to address the universe from 3 different directions. One, obviously, using telescope. Second one, using particle accelerator. And the third one from the underground. So that's the combination we used to try to produce the beautiful set of data that we can understand the universe better. And I was a little worried at the 10-year review that if the review committee would hold us up to the standard whether we have solved any of these questions, we will be an utter failure. But thankfully, they didn't look at it this way, and they really appreciated what we have done over the 10-year period. So my staff actually put together many, many pictures over the 10 years and into a short video clips. I'd like to show that to you. Oh, my hair was jet black back then. And this was a press conference on the launch of the Institute. It was an opening symposium, and already back then, David Gross was here. And Shinton Yao was here, and they came back for the occasion today. This was our first building where we had actually a small gathering back then, but science has already got started back in this building. And we have been very active in outreach from the very beginning, which actually created a lot of public support for this institute. It was actually quite critical for us. Kamioka is a place where many of our friends actually spend their life in doing research. And this is the first year anniversary. And a small group, but was already very international. And this is the moment when the membership of the Institute had more than 50% international, and that was unprecedented in Japan. And our staff have been working very hard, not only to support us, but has also made a lot of impact on the way university operates. So they have received 4 awards. You see actually all 4 pictures. The satellite facility in Kamioka was completed then. And this is actually launch of the Berkeley satellite so that I could continue being the director of this institute. You see, Junichi Hamada is looking over the chancellor. This is the inauguration of the building. And this is the ceremony for the opening of the building. And you see George School sitting on the first row. Well, Mark Bagans must be happy to see this. So eGas is an initiative really started at this institute in Kamioka. And this is the 3rd anniversary. So it has grown quite a bit since then. And again, David Gross came back for this occasion when IPMU was placed on the organization chart of University of Tokyo as part of the Institute of Advanced Study. We also had a fortune of getting a 2nd building and more office rooms. And the PFS is a project that's actually very important for our institute. It started with a small collaboration, now has grown to more than 100. And we've been reviewed very well. So this is the moment when the Japanese government gave us a top mark after the interim review. And a lot of activities got started. This is a new lab that was built on the 1st floor to produce the silicon Buddha detector for Bill 2 experiment, and then Kavli Institute. That was also a very happy moment to see Fred Kavli actually next to the monument. HSC is a new camera Subaru telescope that's also instrumental for science. And out of this camera, we had this beautiful image of Andromeda Galaxy. Again, our staff won the 2nd award for their impact on the business practice at the University of Tokyo. And this is one of the press conferences. Some of them are actually back here today talking about the gravitational lensing as an explanation of apparently very bright supernovae. And this is, of course, a daily phenomenon you see at the tea time, but it's also very important for our science. I had a fortune of being invited to speak at the UN headquarters, actually talking about IPMU. You'll see that later. And we were also very happy that the government decided to continue funding for yet another 5 years that started this April. And this was a very happy moment when Kajita won a Nobel Prize. He's going to speak later today. It's the 3rd award for our staff for the business transformation. And this is the last year. Look how much we have grown. This is the 4th award to our staff. There's a new lab set up for Lightbird and other CMB experiments. Very exciting development. More happening on eGATS. That's a super cameo candidate that gets actually filled with gadolinium actually hopefully next year. The Buddhist text construction is going very well now. And this is where we spend a lot of time together. So, it says our challenge has only begun, and that's exactly right. So that's the 10 years of our institute. It's been wonderful. And another person who is back here, I believe, actually created a video on how our building got erected in just 9 months. Starting from scratch, that used to be a volleyball court. Now they actually erected this building in just 9 months, which is unbelievable. And that's how we now have this fantastic building, which we all love. And I would like to emphasize that our institute is actually very young. So this is the way membership grew over the 10 years, but we have gotten just slightly younger than we started. And the government did a study on international visibility of the institute. They picked random authors of journals, asked them if they knew the name of the institute, name of the director, they knew what the research scope is, if they knew this was a Japanese government initiative, and its highest bars belong to us compared to all the other 4 centers in this WPI program. And we've been also very proud of how well our young members have done. So for postdoc positions, about 10 to 15 every year, we receive about 700 applications every year. More than 80% come from outside Japan. Cumulatively, we hired about 140 postdocs so far. 107 left because their terms expired. And 44 already landed on faculty jobs somewhere in the world. That's an amazing track record. And vast majority of the rest move on to other wonderful postdocs positions. And what Japanese government likes is the fact that many of our former members, many of you are actually here today, have moved on to other faculty positions in Japan. So the international nature of this institute is now spreading out to the rest of the country. Number of publications has been also steadily growing. And this is sort of the impact factor, which we all hate to look at these numbers, but they have to see it. And we do pretty well compared to Institute for Advanced Study, Kavli Institute for Theoretical Physics, and so on and so forth. And this is another way of looking at it. And what they really liked is this high fraction of the international joint authorship. But of course, this is all about science. And this is the area of the research we propose to embark on. And we can cover entire mathematics. We have very heavy focus on geometry and representation theory. In theoretical physics, we focus on particle physics and astronomy. And we have these 3 approaches I mentioned earlier. And already at the proposal, we said that we need to involve statistics because we're heading into the era of big data. And we also proposed to create these kind of synergies. But over a 10-year period, it so happened that we created a lot more together with the condensed matter physics, which we didn't actually anticipate. And already from the early stage, there had been a lot of exciting science results. And of course, this is a random pick. I apologize for not covering your favorite subject, but this is sort of random pick. I would like to actually pick from some of the older slides. For example, Ken Nomura did something very interesting. So Tycho Brahe observed supernovae back in 1572 before the discovery of creation of the telescopes. And obviously there were no quantitative data. People didn't know what kind of supernova that was. But he and his collaborators actually found a way of re-observing it by an echo. So the optical light that came straight to Earth arrived in 1572. But there is also light that gets bounced back by dust cloud that arrived only in 2008. And they could tell that because the particular way this image actually moved because of this reflection. And then they could even do spectral analysis based on this echo of supernovae, and that actually turned out to be type 1a. T2K experiment really builds on the success of a Nobel laureate, Kajita, that discovered the oscillation of neutrinos, and hence neutrinos have finite mass. And after this institute started, this experiment, we joined them, discovered a new mode of neutrino oscillation that was a different mode from what Kajita discovered back in 1992 and 98. And they led to most precise measurements. And just this year, Mark Hartz, our assistant professor, was chosen to present the result out of 500 people collaboration at a press conference, which was the 2 sigma effect of CP violation. Of course, that's not considered to be discovery yet, but that really shows that this experiment is doing well, and also our members are doing very well. And we all love this tea time every day at the interaction area. And one sort of favorite story I tell people is that the work by Robert Quimby and company. So one day, there was a group, primarily based in Harvard, claimed that they discovered a new brightest type of supernova. And we hired Robert Quimby back then because he had discovered the superluminous supernova that was the brightest supernova yet. So obviously he was puzzled and curious, looked at this paper, and started to talk about this at the tea time. And even though this was indeed bright, the light curve, the way it brightens up and fades, looked exactly the same as the type we were familiar with, normal type 1a supernovae, just that it looks 30 times brighter. So what's going on? Well, mathematician, Marcus Warner, in this case, actually claimed that this could be a gravitational lensing, because if the gravitational lensing happens due to a foreground galaxy, and that would act like basically a magnifying glass, that would make the supernova apparently look brighter. But of course, even though this is mathematically possible, what are the chances that there's a foreground galaxy exactly along the line of sight towards the supernova in this big universe, and nobody noticed it before? What are the chances of that? Well, the Oguri actually came in, and he's a physicist who knew how to handle big data. He just quickly asked, how much data set they had, estimated on the blackboard, and came up with the answer that, well, in this big data set, maybe 1 is quite possible. So they wrote the paper right after the tea time. So I understand. And after supernova faded, 2 years later, they re-observed this galaxy and could prove that indeed there was a foreground galaxy. And partly based on this kind of work, all of them got promoted to faculty positions elsewhere. So this is the galaxy, image of the galaxy, and you can't really tell that there is a foreground galaxy. But you do need that in order to see this gravitational lensing effect. The supernovae actually produce multiple images you don't resolve so that it actually looks brighter because of the gravitational lensing effect. So these are multiple images they could fuse together to make it apparently brighter. So what they did is take a spectrum. And this is oxygen doublet. So this is the line from the host galaxy. But lo and behold, there was another one at lower redshift, meaning closer, and that's an evidence of the foreground galaxy. So this got a lot of press. And I particularly like this article from the Asahi Shimbun, that's a major newspaper in Japan. It talked about the mechanism for apparently bright supernovae. And it talked about Harvard theory and Tokyo theory. And it says, this is the right one. We won. And it also covered in many other international media as well, actually more than 80 of them. There have been a lot of work that is at the interface between physics and mathematics. This one by Eguchi, Oguri, and Tachikawa, and 2 of them are actually our members now. And I didn't know that there was a journal of experimental mathematics. It's very interesting. But they came up with this mysterious connection between the K3 surface as a hyperkähler manifold, a 4-dimensional special space, and largest discrete group of Mathieu group M24 using string theory technique. Then this really launched into a new area of mathematics research. I myself am proud of producing some important papers, I think, was chosen as the editor's suggestion in the Physical Review Letters, where we solved 50-year-old mystery why Goldstone theorem of spontaneous symmetry breaking doesn't work in certain systems, and that was in collaboration with condensed matter physicist. And as a result of this paper, he actually received the Yukawa Commemoration Prize last year, so this was already highly regarded. And during the course of this research, I got really a lot of help from local mathematicians. So having mathematicians nearby is really an important thing for theoretical physicists. And mathematicians can sometimes help physicists, and they write joint papers on physics. Or some physicists help mathematicians to prove mathematical theorems. This happened just this year, so it really does go both ways. And we are also trying to produce a very important piece of data by looking at the telescope and looking at the night sky. And we are trying to understand what is the fate of the universe. That has to do with the nature of dark energy. And for this purpose, we need to cover a lot of data and a lot of area, a lot of volume. And for this purpose, Subaru is indeed the best telescope in the world. So we already built the world's largest digital camera that has more than close to 1 billion pixels. It weighs 3 tons. And now we are in the process of trying to build this next generation spectrograph, and many of people here are working together on this. And this combination would be really a world-leading project, and it's getting more and more exciting. So this is some of the early images from this new camera. And this is the picture taken by the Hubble Space Telescope. And this is a picture of using this new camera on Subaru telescope. And on Hubble, they took 500 hours to take this picture. On Subaru, it takes only 2.5 hours to cover the same area in 3 colors because of the wide field of view. And using this kind of data, some of members already produced a 3D map of dark matter, which goes all the way back to redshift of 1. So correlation between dark matter and galaxies is going to be interesting science, and we'll see more of that coming. And interaction between astronomers and particle physicists also created a new idea on this idea that the certain range of black hole could be a candidate for dark matter because it has to do with the TV scale physics, which is just about to be probed in accelerator-based experiments. So the graduate student Nikura and many others have actually pointed the telescope to Andromeda. They read it out every 2 minutes to see if there's any microlensing event happening due to the passing of the black hole in front of one of the stars in Andromeda. And they could exclude a swath of parameters using this technique. And this data coming out from HC is so beautiful, and we actually learned from the Princeton people that it's worthwhile to actually hang it on a wall. And when you actually go to the building later this afternoon for the ceremony, you're going to see the result out of this work that happened just last Saturday. That was a lunch break. It's beautiful. And this is the way it looks. And once you get there, I'm sure you love it. And we've been also very active in outreach. And one example that actually even won an international award is what Hiroshi Oguri did. And this is actually a movie created for the dome environment at a planetarium. And it's about string theory. So that weird guy that was made of strings is supposed to be the theory of everything. He actually tried to escape our pursuit, but the scientists always follow him along. And this is actually a very exciting movie. It won an international award. And as the video said, I was very fortunate to be invited to speak at the UN headquarters. There, I spoke about this fact that kind of research we do is really common to the entire humanity. So this kind of science will bring people together, even from conflicting nations. And I talked about examples where people from Israel and Iran, Pakistan work together and so on. But at the end of the speech, I talked about this institute. So let me play that part. To make it clear that sorry. Let me start again. Oh? The I found in Japan is open to anybody, irrespective of their origin. To make it clear that institute I found in Japan is open to anybody, irrespective of their origins, I named it the Institute for the Physics and Mathematics of the Universe. Laws of physics and mathematics that describe these laws are not applicable to the entire planet Earth, but also throughout the whole universe. One day, I hope to see a job application from a different planet. I would think it's only a matter of time. Thank you so much for your attention. So look carefully at the job database. You might find an application from another planet. And we've been getting a lot of advice from External Advisory Committee. Many of the members are here today. And this is one text they wrote in their report back in 2016, and that actually made me very happy. It is fair to say Kavli IPMU has been remarkably successful within the context of the WPI institutes at achieving the goals it established for itself at the initial outset. In particular, the institute has developed a truly international reputation as one of the leading centers in the world in the fields that it represents. It is especially unique in the degree to which it has coupled pure mathematics to the topics of physics, cosmology, and astronomy. As expected of WPI institutes, Kavli IPMU has also led the way towards system reform, challenging the standard norms in Japanese academia. This has had a dramatic effect on the University of Tokyo, resulting in the creation of UTS, University of Tokyo Institute for Advanced Study, among other innovations. It remains to be seen whether those reforms will also be reflected at other Japanese universities, but the demonstrable success of Kavli IPMU will clearly help to make the case, and indeed, many of the innovations we created at this institute have spread to the rest of the university system, most notably, for example, a joint appointment. I am the first example at the University of Tokyo with Berkeley. Now 72 people exist at the University of Tokyo system. Now it's widely accepted by other Japanese universities as well. And of course, we don't stand still. We are getting four new faculty members, and I'm very excited about them. One, Hiromi Yokoyama, working on science policy and communication. That's a new area for us. Tom Melia just arrived the last month. Works on particle phenomenology, but very strong connection to mathematics. Yukari Ito works on Mackay correspondence and had arrived also last month, and right now on a split appointment, but become full-time later in 2 years. And Hikaru Nakajima is going to join us 100% next April, and this actually makes this institute incredibly exciting and strong. We also revamped our PI-ship, so we added many of the on-site faculty members to the list of the principal investigators, and also there are some off-site people like Eiichiro Komatsu, Yasunori Nomura, Yanki Kim, Shigetaka Moriyama, but they are committed to spend about 1 month every year. Fortunately, or very unfortunately, one person we selected, Fabiola Giannotti, became the Director General of CERN, so she had to drop out. But anyway, so interesting thing is that, again, we are younger than we started 10 years ago. And so only one slide about the future is this. So university has worked very hard to make sure that we can keep going on. And so up to this year, by the effort of university, to get working very closely with the Ministry of Education, we secured about 9 oku yen, it's about $9 million, compared to the initial WPA funding of 13. We're almost there to keep us going at the level we anticipated. We now have 10 permanent positions from the university, additional 13 positions from MEXO, altogether that's 23 permanent positions, 9 permanent staff from the university, and we've been paying $2 million every year to pay back for the building, but that's now over, so that's another $2 million worth of saving. And just this year, university put in another budget request to ministry as its top priority, and so it's very likely that something will come out of it. And hopefully that would make up the remaining about $4 million missing to sustain us at the level we operated over the last 10 years. And it was also a very moving thing for me that the University Budget Committee looks at every proposal from different departments. They are in some sense in competition, but they ranked our proposal the highest. So that's a clear sign that it's not only that we enjoy our institute, but university-wide, it seems to be well appreciated. At the latest review, the Executive Vice President Koseki presented the view of the university on behalf of the rest of the university as well as the president, and talked about this timeline. So this is the way the WA funding would end, but this budget request would ramp up until 2022 to make up this remaining $4 million. And so this is a new scheme to support us after the WPI funding actually expires. And it's very clear. They would like to make Kavli IPMU permanent as an international institute of excellence. They think that our institute is the best model for establishing a new institute. And this is actually ranked the highest among the other proposals from the university. And it's based on 3-way financial sources from the ministry, from the university, and Kavli Foundation, of course, helps us to embark on the risky and short-term research, and that combination is crucial for us. And university can, in principle, provide even more resources if we actually keep performing at the top level. So this is how he concluded. We'd like to capitalize on the amazing success of Kavli IPMU. And this matches well for the vision of the university. The university wants to rather expand rather than shrink us. We spearheaded many system reforms which are now adapted by the university. And the university now putting together a plan to strengthen the financial base so that they can support us with no problems. And as one concrete example of this, we now have a brother or sister. The WPI program created yet another institute at the University of Tokyo. This one is actually on neuroscience. And Takeo Hensch is at Harvard, so he's going to do what I've been doing, namely he commutes back and forth. It's a little longer to Harvard than to Berkeley, but anyway, he's willing to do that. And so this is actually a very interesting combination of human intelligence and artificial intelligence and clinical research. And he's very keen to work together with theoretical physicists. So if any of you have any interest in actually getting involved in discussions and working together with them, that would be actually wonderful. So we have now a brother and sister. Finally, just in case you're wondering what the heck this is a traditional Japanese candy, so you can eat them. And this video shows how it was made. Now you can see IPMU. Now Kavli. 10. There's a blue coating outside. And you're gonna stretch it, make it thinner. And they'll cut it. There you go. Enjoy the candies, and we look forward to the next exciting 10 years. Enjoy the meeting.